Hi, this is Peter with CalcBook, and today we're going to be looking at a timber connection design, and specifically looking at a lag screw connection, and we're looking at a group of lag screws in lateral. So just a quick recap on our timber design, right? We use the National Design Specification, also known as the NDS. We have two booklets that we refer to, the NDS spec and then the NDS supplement. So for the spec, right, that gives you your design procedures, capacity equations, adjustment factors. And we can also determine what we're going to use for our load direction, whether we're in lateral or withdrawal, and then the type of fastener, right? So for us, we're going to be focusing on dowel type, so bolts, lag screws, wood screws, that sort of thing. The supplement doesn't get used as much for connection design, right? That is going to give us our reference design values for the members, shape properties, additional adjustment factors, specific to the species. But for connection designs, that does not come up that much. So for today, right, we're going to be looking at lateral loading, specifically lag screws and lateral loading. We've done a previous video on a single fastener in lateral loading, but now when we're doing this group design, right, the biggest change here is this C sub G, the group action factor, which has this long equation, 11.3-1, with several different calculations within it. So we will go through all those different steps once we get into CalcBook and get into the design. So let's take a look at our problem statement. Right, we have a steel plate fastened to a 2x6 southern pine member. It has an end distance of 3 inches. The side member, like we said, is a 1/4-inch steel plate. It also has a 3-inch end distance. We're going to be utilizing 3/8-inch hex lag screws with a spacing of 3 inches. And we've got a configuration here of a 2x3, so we've got a total of 6 hex lag screws. We have dry service condition and a dry fabrication condition. We're going to be utilizing ASD, and the members are loaded longitudinally as shown. And our loading is due to earthquake of 2,750 pounds. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, I've got CalcBook open now, so we're going to click into our timber design, and then we'll click into our connection design, and we're going to go ahead and click on the lateral load on dowel type fasteners group. Okay, so we want to go ahead and start with our dowel type, right? We said we have a hex lag screw. We're going to start with a 3/8-inch diameter hex lag. Our dowel bending yield strength is populated for us, but if you need to double check or you want to maybe change it, you can use this reference table from the NDS table I1. Our total length of fastener, right? We're going into 2x6, so it shouldn't be more than 1.5 inches. We've got the steel plate there, so we'll just say it's going to be 1.5 inches long lag screw. We said we have 2 rows of 3 screws each, and our center to center spacing is going to be 3 inches. Our main member is a wood member, and we're going to scroll down here to southern pine. Our load direction, right, it has to do with the direction that we're kind of pushing and pulling this connection. It's not perpendicular, it is parallel, and then we need to decide whether it's compression or tension. And for us, right, it's going to be bearing towards the end of the members. So we want to use parallel to grain tension. And since it is southern pine, that is going to be a softwood. The angle direction is 0. It's parallel with the grain, so we can leave that as is. Our main member thickness is 1.5, and the width is 5.5 for a 2x6, and our end distance is 3 inches. The next thing we want to do is go ahead and select our side member, which is going to be metal. We're going to use a hot rolled shape, right? Just a flat plate. And the thickness there, we said it's a 1/4-inch thick plate. And we're also going to match the width of the member. We need to update our modulus elasticity here for steel. All right. Last thing we need to do here is switch over to ASD. So we just go to our settings and click on ASD, and we'll click confirm. And that will allow us to update our load duration factor. Because this is earthquake loading, right, we can take advantage of the wind earthquake loading of 1.6. So we'll go ahead and set that to 1.6. And we said we had dry surface conditions, we're not into the end grain, and we have no temperature conditions. So let's go ahead and update our demand, right? We said we're going to use seismic loading. It's 2750. All right, and we're showing that we're at a DC ratio of 0.72, so that's great. Let's go ahead and jump into the calculations and take a look at some of the details. So we are using ASD load combination 10, right? So 0.7E. and then we go into our capacity calculation. So we have some preliminary information, right? We need to reduce the taper, the tip taper off the length of our bearing. Then we can calculate our bearing length, right, which we don't want to exceed the thickness of our main member. So we have 1.14 inches of main member dowel bearing. The side member bearing is just the thickness of the plate. We calculate our bearing strength, our dowel bearing strength for the main and side member, our RE and RT values, our K values that go into our nominal yield nodes for lateral, and we different reduction factors for each of the yield modes. And then we get into our nominal yield mode capacities, right? We've looked at this stuff before, all of our different Z values for each different type of failure mode in lateral. And then we go to our adjustment factors. So most of these are pretty straightforward, but the big one we have to deal with, right, is our geometry factor. So we have a couple sort of preliminary calculations that go into that geometry factor. So we have this factor U, our load slip modulus. This all gets calculated based on our inputs and material properties. We have this M factor. Then we have this area modulus ratio, and that all gets plugged into our C sub G factor and gives us a group action factor of 0.97. We meet both of the minimum end distances, so we just end up with a end distance of 1, our geometry factor of 1. No end grain issue, no diaphragm, and no toenail, so those are all just 1. And the last thing we need to do is check our connection capacity, right? So we multiply all those together. We multiply by our total number of bolts. It gives us a ASD design capacity of 2,667 pounds, which is greater than our demand of 1925. So we have a DC ratio of 0.72. So that is a lateral loading of a group of fasteners in CalcBook. We hope you enjoyed the video. If you have questions or suggestions for other videos, please let us know in the comments below, and we'll see you next time.